Hello folks, and welcome to this lesson on the Arrhenius Equation. By the end of this lesson, you should be able to analyze the graphical representation of the Arrhenius Equation in its linear form and determine and evaluate values of activation energy and frequency factors from data using the Arrhenius Equation. So over the last little while, we have talked about activation energy a few times, but how do you actually figure out how much activation energy is? However, how do you actually find out what activation energy is? Well, we know that activation energy is going to be dependent on the reaction itself. So depending on the type of reaction, how many particles are reacting, etc. and so forth, it's actually going to change depending on what the reaction is. And you also know that activation doesn't really change if you change the surroundings. The only thing that'll change activation energy is whether or not there is a catalyst. So that means no matter what you change in terms of the surroundings, the concentrations of everything, activation energy itself isn't going to change. So let's take that last bit and take advantage of it and see if we can find out a way to determine what activation energy is for a reaction. So before we go into the other details, I want to remind you of Maxwell-Boltzmann diagrams. So you're going to have all of your particles, all of them are going to have a particular distribution, and we know that there is a certain amount of kinetic energy that all particles need to have before they're able to react. So any of the particles that are above this activation energy are going to be capable of reacting. Now we also know that if you do something like, say, change the temperature, then this distribution is going to change. So, for example, if we're going to lower the temperature, it'll look a little bit more like this. And there will be fewer particles that have enough energy to actually react. So if you have fewer particles that actually have to have the energy to react, the reaction rate is going to go down when you change the temperature, when you lower the temperature. Now you also have another value that you know that will change if you lower the temperature. And that's that K value, that's your rate constant in your rate law. So we know that this EA value is always going to stay constant if you're just changing the temperature. So why don't we take a look at the relationship between the temperature and the rate constant and see if we can find some kind of a relationship that will get us to that activation energy. Now, when you find out that data, you have this reaction happen at different temperatures, and then you find out what that rate constant is in each of those temperatures. There's a little bit of an issue in that it's going to give you a curve, and curves are not very convenient when you're trying to find out what the relationship is. And so something that you can do to better find out what the relationship is called line straightening. So what you do is you change the variables and then you graph it, and whatever gives you a straight line can give you that relationship much more accurately than trying to figure out what a curve looks like. And so while temperature versus the rate constant is going to give you a curve, if you actually graph 1 over temperature and ln K, that gives you a straight line. And the straight line is going to look something like this. Now the nice thing about a straight line is that it is very easy to get an equation for a straight line. You basically do your whole y equals mx plus b thing. Now from here, y is going to be basically ln K. You're gonna have some kind of slope, and it can be made out of certain values. Your x is your 1 over t, and then you have your y-intercept, and that's probably going to mean something as well. So let's take a look at what each of these different components are. Now it turns out that that slope is actually the negative of the activation energy divided by R, and that R is the same gas constant that you used back when we were talking about gases a lot more. Now this negative sign is there because, as you can see, the slope is negative. Activation energy is going to be positive, and your R value is always positive as well. Oh, and by the way, the reason that you see that R value having the units of joules and all of that in your data booklet is because of this whole relationship. Now, this y-intercept does have its own meaning, but for now we're just going to call it ln A, and I'll go over that in a few moments. So here we go. We have a relationship between your temperature and your rate constant. We can use it to figure out your activation energy. So once again, here's that Arrhenius equation based on the equation of the line that we got before, and we can rearrange everything to look like this, and depending on which situation or what type of question you're looking at, either of these could be more useful than the other. So just in case you've forgotten, here is what all of those other bits are, and now let's talk about A. So A is referred to as an Arrhenius constant, or in some cases it can also be called the frequency factor, and it can also be called the pre-exponential factor as well. The unit for the Arrhenius constant, or that frequency factor, is going to be whatever the unit for K is. And of course, since the unit of K depends on the reaction and the rate law itself, it's always going to be different. Now the whole point of A is to take into account the frequency of collisions and the probability that the collisions have the correct orientation to occur. But the important part is, at the end of the day, it is another constant that you can get in relation to these reactions. It is going to be unique to the reaction and isn't going to change based on the surroundings either. Alright, here's a potential practice problem that you can get. Pause the video and see and take a read at it. Alright, so here we go. These are the two different formations of that equation that we have to use, but you might notice that there's a bit of a problem in that you don't actually have that Arrhenius factor, or rather the frequency factor or the Arrhenius constant. So what do you do instead? Well, we are going to take advantage of the fact that we know the slope of that line from that graph that you would get when you were doing these sorts of experiments. You know what the slope of the line is, and you also have basically 2 points on that line. So if we find out what the slope between those 2 points of the line are, and you have the slope of the line that you can refer to, then maybe this is solvable. So let's take a look. So remember that when you're trying to find the slope of a line, what you're basically going to do is the rise over the run. Or it's the difference in your y values versus the difference in your x values. Now, based on the graph that you draw, the difference in the y values are going to be ln k2 minus ln k1. Because remember, the graph is based on ln values when you're looking at the y-axis. And in a similar fashion, the run is going to be t2 minus t1, but it's not t2 that was graphed. It was 1 over t2 minus 1 over t1. So now you have an equation. We basically know all of these numbers. We also know that gas constant. So that means we have one equation. We have one unknown. It's solvable. So put in your values and solve for activation energy, and you're going to get, with sig-digs, that it is 200 kilojoules. Now, something that a question might do to throw a wrench into the situation is that instead of asking for what the activation energy is, they might ask for what the change in rate constant is instead. So they give you the activation energy, they give you the different temperatures, and then they ask you to find out what the difference is going to be. Now, the thing is, based on the stuff that we have, finding the actual K2 minus K1 is going to be difficult when you're trying to figure out what the difference is. So yeah, if you take a look at all of the numbers that we have, all of the things that we have, unless you're given that frequency factor, you're not going to be able to find out what K2 minus K1 is. And actually, when a question is asking you for what the change in rate constant is, they're not actually asking you what K2 minus K1 is. What they're actually going to be asking you for is K2 over K1. So it is still a comparison, so you are sort of finding a change, but it's not the usual change that you're thinking of. Now this is actually solvable Because if you take a look at what we have here, then the premise is going to be you have your temperatures, you have your activation energy, and then you have this, and you can isolate for this. Now, if you remember how logarithms work, this is going to be equal to the ln of k2 over k1. And so basically after that, get rid of the ln, and then you will be left with k2 over k1. So there you go, that's the end of this lesson. I'll see you next time.